start this lecture. Now that we know quite a lot about ocean models, let's relax a little bit and speak about assessment of these models. So in particular, we'll have two lectures about model validation, model assessment in this summer school. And this first one is about focused on the assessment of high resolution regional ocean models from the multiplatform observations. And mainly will be centered in the Western Mediterranean Sea with the local framework of operational oceanography here, in particular at SOCIB in Godae. And the other lecture will be given by Fabrice Hernandez next week. It will give you a more, I think, high-level overview of the coordinated activities in model validation with Godae. Okay, so I will begin with a brief introduction and some thoughts about the model assessment, and then we'll enter into more details. So what I wanted to say that now regional operational predictions over extended area, let's say 1,000 kilometers, are affordable with a high resolution of 1 kilometer. And so that now we are able to run this operational model and also reaching the coastal zones in particular where there is a lot of applications. And this is thanks to the community efforts that have been made in ocean modeling science, the maturity of large-scale systems that allow you to apply downscaling approach, which take the initial conditions and boundary conditions from these large-scale models, and also you have an enhanced computing capability. So these systems have been implemented in many regions of the globe, and they generally represent a wide range of spatial control scales. So you have from the mean, you construct the mean circulation, but also the mesoscales on the coastal circulation, like coastal eddies, river plumes, upwelling, and so on. So if you're interested in seeing the list of these models, the Godae OceanView coastal and shelf sea testing provides you a system information table collecting all this kind of information. So it's really over all the world ocean, all continents, you have a lot of this model implemented. And this model, what you want to do is to address the need for model products, both for science and for decision making. So there is really a need for these model projects. Models provide you the four-dimensional view of the ocean, or at least an approximation. And that's really what people want, because it's not really accessible through observations. So use this for science to let's say, investigate filaments, eddies, or fluid circulation. You want them to force this to ecosystem models. We're interested in knowing, for instance, here in the Balearic Sea, why the bluefin tuna migrate every year and spawn south of the Balearic Islands. That have to do with oceanographic conditions that you can represent in the models. Why do you have jellyfish some years on green beaches and other years you don't have any jellyfish? You have to respond to emergencies, able to provide some prediction of drills in the oceans for search and rescue. Also, you might want to see if there is some accumulation zones in your regions to apply to plastics, to the drift for larvae. So there's really a lot of applications, and really we ask a lot to these models to represent a lot of different processes, and there are a lot of multiple potential users. So there's a need clearly for model assessment. But let's deal with important challenges with this. So first, we have a limited knowledge of the state of the ocean, and especially at the small spatial scales. That may be very important for the different applications. The models are four-dimensional, all the variables are there, and the observations are limited to specific variables and in a specific, a limited number of dimensions, if you want. And also, the observations are affected by some errors. So the model assessment you may do, what you will do is inherently partial or incomplete. So you have to keep that in mind. Then the model performance, it will depend on the region, the depth, the variable, the scales you consider. So this is another aspect that you may have multiple outcomes of the model validation. And third point I want to raise is that you have to choose the metrics if you want to quantify the model performance. So which metrics will you use? Different users will need different metrics. And also with the high resolution you have in the models, if you use font-wise comparison, you may have other problems and other biases in your metrics. So that I will comment this a bit later. Okay, so just to sum up this first introduction, it's multifaceted problems, and there is no single measure of model performance. It will be a multi-dimensional problem. So in this aspect, we will look at, consider how the multi-platform observing system, so it's the modern oceanography. Remember the change of paradigm in the ocean observation, what it was like in the first day. Say that we're not anymore in the framework with a single ship having very confidential data, but we have the network of multi-platform observing systems providing data in real time and open data. And so we have data of different variables at different scales, and these offer really a new opportunities to evaluate these models. So this is really the objective of this study is to illustrate this idea in the framework of the Western Mediterranean Sea. So we present the SOCIB regional observatory with the multi-platform observations and the different models we are running. Then we have a short section on how to quantify model accuracy and the problems that are related to this, and then illustrate the multi-platform model validation. Okay, so first of all, I just tell you a little bit of the Western Mediterranean Sea so that you can understand then what problems we have. So we are considering really with our model this area, the Western Mediterranean Sea. I represent here the animation of the Sisyphus salinity. So salinity has a really variable with a high impact in this sea. You have entrance of less saline pressure water in the through the Strait of Gibraltar. Then it flows along the coast. It has a giant current. It then comes back after having transited through the eastern basin with a lot of evaporation. So it comes back much more saline. So you have really different gradients of salinity there, and that generate very intense mesoscale. And if you see that the Balearic Islands are just in the middle of these kind of frontal areas, they are important water mass exchanges along across the straits, Rissaga channel and Mallorca channel. So this is what we're really interested in monitoring and modeling. So just to put the names on the main structure, you have we call the Alvaran gyre. When the jet enters here through Straits of Gibraltar, we have two gyres. You have the Algerian currents flowing along the coast. There is a lot of instabilities here, a lot of high mesoscale activity. And then you have the northern part, you have the northern current along the slope, which then deviates, bifurcates into Balearic current, and then some flows across the section. And this is the kind of signal you can see from altimetry, which shows you, allows you to detect eddies, to track, to see the propagation of eddies in the Algerian basin. Okay, that's not all. You have also winter convection sites here in the basin. You have deep water or also intermediate water that are formed in different sites, and that also flows southward, and you can find them in this Rissaga channel. There is a whole overturning thermal circulation in the basin. So that's why the Mediterranean Sea is often considered as a radio scale ocean laboratory. The internal Raspberry radius is the order 10-15 kilometers, so smaller than what you can find in the global ocean of the same latitude. And so you have a lot of processes that are relevant or you can find in the other oceans. Another particularity we have here is the presence of mid-tsunami, occurrence of meteor tsunamis in Ciudadela, the ARGO in Mallorca, so just 60 kilometers from here. Okay, so that's a bit what we would like to address with the oceanography, observing and forecasting system here in the Balearic Islands. So from these considerations, SOCIB was built. It's a coastal observatory in the Balearic Islands. So it's a multi-platform observing and forecasting system. It goes from the nearshore to the open ocean and driven by science priorities, technology, and addressing societal needs, okay, with open data principles. So it was really born from many years of work at IMEDEA, and then on this line it was born as a separate institution, but in very close collaboration with IMEDEA. It's really operational since 2014, quite a young institution system. So there is a lot. If you enter the website, you can see all the different platforms, and that's what I will describe more in details with the model validation. Just to illustrate the map of current deployments, right now this is a map from yesterday deployment. You have a glider that is doing the transect in the Ibiza channel. You have some ARGO floats here that contribute to the European program, and you have some turtles here that are doing some swimming inside the edges. Okay, so from the modeling part, what we have mainly the ocean circulation model, which is called the Western Mediterranean operational model. It's a regional configuration of the ROMS model. It has a horizontal resolution of 2 kilometers, and it's a downscaling of the CMEMS larger scale Mediterranean model. So we have 32 sigma levels, and we use high resolution atmospheric forcing for this model from the Spanish Meteorological Agency with a 1 hour and 5 kilometer resolution. You also will also have rivers in this configuration. So just to show you a streamline that was made by Romain Scudier last year. And so you can see the richness of structure you have in this model. So you really have represented a small scale, the mesoscale and small scale eddies. And this will, of course, constitute a challenge when you want to validate this model with the observations available. And to link with the previous simulation, previous presentation, I show you here the video of the relative vorticity, surface relative vorticity, in the southern part of the basin, the Algerian basin, where you see the evolution of vorticity structures, anticyclonic, the propagation along the coast, the detachment of the structure, and you can also appreciate the difference between summer and winter periods that were also highlighted in other presentations. For instance, here, November, you begin to have really smaller scale structures appearing here. Okay, so that what we have to represent both, we want to have both the subbasin, the large scale, let's say, circulation. We want to represent the mesoscales and also go to the coastal scale. We also interested in having representation of the water mass formation that are important in this basin and the spreading of these water masses. We have two different kinds of simulation. The hindcast mode, it's a free run. It helps us to understand the dynamics, how the model represents the different dynamics. And also the forecast mode that is more constrained by operational constraint, let's say. So we don't have any data simulation in this model at the moment. We have a weekly restart from the MFS conditions. So in the following, I will maybe jump in between these different models, hindcast, forecast, for the model validation. Okay, so let's go back to the topic, which is the model assessment problem. So at some point, you will need to quantify the accuracy, when you compare models and observations, and this is generally done by computing. If you have let's say, vector of observations, you will compute model equivalent to the observations, then compare them, and then you can get some statistical measure of the error. So I just quickly summarize this here. Model equivalent, you may just interpolate in space and time. You may want to filter if you think the scales represented in the observations are not the same that the one in the model, or whatever, doing some box average or whatever. But you have equivalents to the observation, then you compute. Basically, you can compute mean error, the root mean square error. These are really the standard statistics. The cross correlation would give you the coincidence to mismatches in the patterns, in the phase of the signals. Importantly, the standard deviation error, which is the difference in the standard deviation both in the models and observations. You may calculate also scale of the model when you want to compare to a reference simulation, or when you want to compare to climatology, to persistence forecast. And basically, I put that here mainly to show you that there is an important relation between the root mean square error that is very frequently used, and that you can decompose in different terms. So you really, to have a low root mean square error, you need to have a low mean error, to no bias. You have to get similar standard deviation between your model variability and your model and the observations. And if we build a correlation error like this, also you need to have a correlation close to 1. So this is it's interesting to separate the different contribution when you look
instead of considering only a single root mean square error. And this can be plotted in synthetic diagrams like Taylor diagram, target diagram. So nicely you can plot, compare different models, and here, for instance, you have the angle that is the correlation, the distance to the point observation would be the centered root mean square error, and let's say distance to this line would be a standard deviation error. But this is the classical tools that you use in model accuracy that we'll find in different publication papers about model assessment. Okay, so now I would like just to illustrate the importance of choosing the choice of the metrics. And I just consider this example with, let's say, consider that in the observation you have an eddy here. That was a case in 2014. And we had different simulations, which were let's say, sensitivity test of our hindcast simulations. And I plotted here the contours in each of these simulations. And this is the RMS error that you can get with the different cases. This is ranked, this is the lowest, this is the highest. And you see that in the lowest appears when you have the flattest field here, but it's not necessarily the best the best field you may have. This one has an eddy that is quite close to the observed one, but it's not as the right place. So you have what you call the double penalty error. That I mean this score penalizes this because you don't have the eddy at the right place. You don't simulate under the observed eddy, you don't simulate the eddy, and outside this, you observe an eddy, so it's a double penalty. So there you may want, if you're interested in having an eddy close to the observed eddy, you may want to define another matrix. And this is the exercise I did here. So I just transformed this. Imagine what you want is to identify an eddy, so you just select a criterion. In that case, it was the Okubo-Weiss parameter to transform the sea level anomaly field into another metric that represents or not the eddy, so I still have the contours. And then you can even complexify this and apply what we call the neighborhood methods. In that case, you may be interested in not having exact match in space and time, but you might qualify your model if you have in the neighborhood of the observations a right representation of the eddy. So doing this, you can, for every position here in the observations, you calculate if you have an eddy given a certain neighborhood, given an eddy in a certain neighborhood. So for a given distance, you can say whether your model is able to represent some eddies. And at the end, you could come out with this kind of matrices that, according to the distance, this is the number of simulations, so still 1, 2, 3, 4, 5. And you see that they won't be ranked the same manner they were ranked with the root mean square error. So in that case, for instance, the fourth one, which is this one, has the best score, and this corresponds to what you visually see, that there is an eddy at the right place. Okay, and instead the 1 and 2 that have the lowest root mean square error do not really have a good performance in that case. So this is just to illustrate the importance of the metrics when you want to assess your model and think about what is your goal. Are you interested in having an eddy, or are you interested in having a low root mean square error? Okay, in what follows, so I'll go to the third part, which is the multi-model validation. I really won't quantify the model performance. It is more qualitative, and this will be more illustrative of the different possibilities we have with these multi-platform observations to evaluate the models. So, I mean, the basic scheme will be this one. We have these WMOP ocean simulations, and we're interested in taking into account all the available observation in the area to evaluate this simulation. So we have both the near real-time aspect and the delayed mode. So some of the observations are not all available and not with the full accuracy at the near real-time. So you may have another assessment in the delayed mode. What's interesting that in the real time, you really can have some operational evaluation of the model together with your predictions. So what I will do basically is give you a tour of the different different platforms and illustrate what we can get from these evaluations. So I begin with, let's say, the satellite part, even if this one is not only satellite, so it's how do you evaluate the large-scale mean circulation? It's probably the first thing you want to evaluate in the model. So you use the mean dynamic topography. So in that case, in the Mediterranean, this is computed from the time series of sea level altimetry, but not only. It also uses hydrographic profiles and long-term model average in this case. But it is a product that allows you to evaluate the large-scale mean circulation. And if you compare, so you can then correct from the MDT that is a reference for a given period. So you correct with the right mean or the right period to get something comparable with your model period. And this is the comparison we have here. So you see that for the large scale, you properly represent the entrance of Atlantic water, the two gyre. This one is overestimated compared to the model, to the altimetry and the mean. The Algerian current here, and let's say cyclonic circulation in the northern part of the basin. So what you see that the details do not match. You also have to consider that here the details may not really be realistic because of the lack of details or lack of hydrographic profile. So it integrates all this information, but you have areas where you have very sparse data. Another aspect, if you check the color bar here, you can see that the range is the same, but the mean field is not the same here. So this is because the reference you have in your model might not be the same as the one you have in the MDT. It just depends on how you initialize your model, if you have been careful about this aspect, mainly. But what is really important for the dynamics is the gradients you have here. So another aspect that was already mentioned also this morning by Eric, altimeter provides you the time series, so you can really have access to variability at the larger scales. So if you compare, in that case, the mean kinetic energy from altimetry to that of the model, so you see that you may have the right patterns, so it's higher energy in the southern part of the basin, but you have much higher level in the high resolution model. In the mesoscale activity that may represent here, you will have a small scale structures associated to this in the high resolution model. So it's not really fair to compare these two fields because it's not representing the same things. And so quite the same exercise that was presented this morning, you can separate geostrophy as geostrophy. And so if you only compute geostrophy from this field, from the CSOFAS 8 of the model, you reduce the level of eddy kinetic energy. And then you have the problem or the issue concerning the scale, so you can filter these model fields and you get eddy kinetic energy that is much closer to that of the altimetry. So here there is still uncertainty on what is the good filter to apply to have something similar. But the idea here is really when you compare models and observation, you have to understand the representativity and when you interpret the differences might be just due to the fact that you don't represent the same processes in the model and in the observations. So apply the right filter or do the right processing to compare things that are comparable. Okay, so with altimetry, you have these sea level maps. So it allows you also to compute EUFs and those things that are very standard also in the analysis of altimeter, and you can apply them to the model. And you can check, for instance, this is an example for a first mode of variability in this area, representing the southward flow and its acceleration, deceleration with a marked seasonal cycle. So you can check that you have the right mode, difference in the mode. Let's say here you have a structure that is present in the model, but not really here in the observations. And you can check what the seasonal cycle if you apply spectrum to this, or also internal variability in this signal. So you have to complete this with other higher EOFs, but this is really a good tool to evaluate if you get the right mode and if you get the right phase of this mode and frequencies. you can go, with this signal, you can go even further, and you can track eddies, for instance. You can track eddies in the altimetry, and you can apply these codes also to the model. So this is an example that the work in progress by Simon Reith and Evan Mason. And so if you just track eddies and plot all these eddies as little points, the red will be, you can separate cyclones, anticyclones, long-lived eddies, long-lived anticyclones, long-lived cyclones, and you can compare these maps. So you see that you have a lot of eddies everywhere, and you need maybe some further analysis. So you can compute by box, by year, and having the number of eddies. So this is a comparison with the Siemens MedMFC model. This is not the WMOP, but it's the parent model. And so if you compare, for instance, the map of the number of cyclones per year, this one and the other one, you see that you have overestimation in the model here. And so maybe due to resolution, and also the idea with this, when you use these, let's say, sophisticated analysis of the altimetry, that you really need to understand what are the limits of your tracking algorithm, because part of the error, part of the differences might also be due that you have applied algorithm that do not really represent let's say the real eddies. And this is illustrated here by this plot where 3 different methods were compared, and you see that you have many instances where one of the methods detects an eddy and the other one doesn't detect any eddy. So maybe you have to work at a combination of these methods to have more robust results. So when this is like a continuation of this work, and you can, with the eddy tracking, you could highlight preferred path of propagation of eddies. So this is the case in the Algerian basin. We have like these 2 gyres, and then you can take the altimetry and the different models you have to check if you have correct formation, correct propagation in the model. So this is represented here in terms of Hofmüller diagrams. If you focus on section 1, which is this one, so you see that in the altimetry you have, let's say, on average 1 big eddy per year. In the WMOP, it's not as clear. You have more or less same frequency, but you don't have any match with the eddy with the free run. You see that you are like that. You really need that assimilation here to have this representation of the large mesoscale eddy in the Algerian basin. And you can, for instance, evaluate if you have the right propagation speeds, or do some more analysis once you have identified your eddy trajectories. Okay, so satellite SST is another very rich data set to evaluate the models. You have either the high resolution images can be contaminated by clouds with gaps, or you have also these interpolated products with a high resolution. And this is what I show here, like an example of comparison for a given date 2 weeks ago, where we have, you can see that you have very nice definition of the structures, let's say in the Gulf of Lion here, and that match quite well what you can get in the model. Let's say if you focus here, for instance, on the northern current, you have some indication. You can have some indication from the sea surface temperature. So what you can get is both. If you have some biases in your model, you can identify some problems with air flux parameterizations or the atmospheric models, or even the vertical mixing. This is the case here, for instance. I think in the Alboran Sea, in the western part, we have some overestimation of the temperature, and this is probably due to the lack of tides in the model. The tides are known here to mix a lot, to induce a lot of mixing, and so to reduce the sea surface temperature. Okay, so we go quickly show you the ARGO floats, the situation we have in the basin here. We have 5-day cycles in the Mediterranean Sea, and so it's around 5 profiles per day, let's say 200 kilometers separation between these. And so if you compare every day the models with the data, you can get estimation of how your model does represent the mixed layer depths, for instance, or the vertical mixing. And also importantly, it has information about salinity, which is not a very well observed data. We now have data from satellite, but in this basin, we haven't really managed at the moment to exploit them. Okay, so fixed station is another very important data to provide very high level, very high frequency information of different variables. Can be equipped with a lot of different sensors, temperature, salinity, currents, also providing you data at depth. And so you may have very long time series, allowing you to identify the model accuracy at really very different scales, temporal scales. So if you plot, for instance, the last week, last month's time series here, you can see that you have the drop, the mooring will be in red and the model in blue. You have a general drop of the temperature linked to the seasonal cycle. You have small weather scale, let's say, events. And you have also an estimation of the diurnal warming that you may want to represent in your model. If you take longer time series, you can evaluate your seasonal cycle. You can evaluate how let's say the heat waves are represented in your model or particular events during the year. You have data along the vertical, so this is just an illustration of what we can do. You can analyze it in terms of US mode also along the vertical. The V will be in red and the U in blue, and for instance can allow to highlight that the model represents kind of decay of the velocity in depth that is not really in the observations in the first 120 meters here. So you know that we may have an underestimation of the variability at 100 meter depth. At the same time, you can check that let's say the third mode, the barotic mode, have quite the right structure in the model and the observations. So this is additional information you add on the knowledge of the accuracy of the model. So I will, while I'm here in the fixed station, I will just jump on the meteo tsunami problem and show you this is really a regional hazard, a regional specific problem we have here. So the meteo tsunami, or it's also called Rissaga here, it leads to really large, up to 4 meter, high frequency sea level oscillation in the harbor of Ciutadella, which is just here in Mallorca. The Poyensa, we are at the moment we are here, so it's very close. It's generated by atmospheric waves, atmospheric pressure waves. And so these generate a response in the ocean, a barotropic wave, that is then amplified over specific conditions of velocities, of directions. This is amplified over the shelf between Mallorca and Menorca, and this is then amplified a second time inside the harbor of Ciutadella. So what is important here is to represent the atmospheric pressure oscillations. We really need a high resolution, to 10-minute phenomenon in the harbor, and the response in terms of, it's mainly a 2D problem, barotropic problem, the response in the ocean. So to do that, we have implemented this ocean atmosphere modeling prediction system. It uses a two nested grid of the wharf, and then the outputs with the very high resolution force 2 grid of ROMs to really represent the very fine details in the Ciutadella harbor. So it's a very practical implementation of these models to respond to a specific problem. We have as I say, I insist that we really need a very high temporal resolution. And so then for the validation, we really need from the fixed station, very high resolution to see if we really have this oscillation. For this, we have a network of fixed station here, measuring both the atmospheric pressure over the different islands to also allow to characterize the propagation and the evolution of these perturbations and the sea level with the bottom pressure sensor here in Ciutadella. So here, for instance, it was the case in August 2015. You can see that in Ibiza you have no signal, and then you see how the signal gets until Ciutadella, and you can assess how you represent it in the model. So you generally don't have a perfect match, but you have some oscillations in the best cases at the right time with the right amplitudes. And then you really validate with the time series, with the bottom pressure time series, the ROMs, and the observations. So in that case, we had a very nice match in the amplitude of the Rissaga, which is the problem, which is the most problematic aspect. You have time series of observations with this fixed mooring, so you can really assess the frequency spectrum of the data and the model. What's important here is to represent this 10.5, 10.6 minute maximum in the spectrum. So you have amplification of the signal at this frequency, and we're happy to have this in the model, so it gives us confidence that we can go forward and amplify at the right frequency in the harbor. Okay, so it was just a little detour with this meteor tsunami forecasting system, and let's go back with the WMOP simulations. Surface drifters is another platform that is very useful to provide you information on surface circulation. It's a Lagrangian platform, so it follows the current. But if you have sufficient data, you can also analyze this in terms of Eulerian framework by boxes and taking the mean, for instance, in each boxes, and you can even compute the kinetic energy. So it was an estimation of eddy kinetic energy in the basin from the 20-year or 20-year drifter data, and you see that you get numbers that are quite closer to that you have with the full model. The estimation I provided you at the beginning, and much more than the altimetry. So it's complementary evaluation of the realism of your variability here. So with given experiment, you can also apply this Eulerian analysis and get estimates of the velocities in different places. The main problem here is you're really limited by the amount of available drifter to be able to compute really good estimates in the Eulerian framework. So mainly, what you have to do is generally a Lagrangian analysis of this. So you're looking at the tracks of the drifters, and I show you here an example of the capabilities of these to give us new insight into the model performance. So these were two drifters that were launched in 2014, and below in blue, these are the velocities of the model in the WMOP model. And what is interesting here, these drifters really highlight the existence of a gyre here, a coastal gyre, that is also present in the model, and that we won't have any more way to validate without this instrument if we don't have any radar here in the area. So useful to detect the small-scale coastal features. And so once we are with the coastal feature, we can also try to get some indices about the impact of downscaling. So that's what is presented here, the same figure with the velocities of the parent model. And you see that you don't have the resolution to get you don't have to get the resolution to get these features, and it's something really contribution of the high resolution model. So you can also launch particles into your model. So the way you do that generally is to launch clusters of particles. You had some diffusions at every time steps. These are the particles in red from the model. This is a real drifter trajectory in black. And what was interesting in this experiment that you really have a very good match in the terms of velocities in the model, and you also see this oscillation, which is really due linked to the sea breeze that you have here in the Bay of Palma. This is Palma with a 10-kilometer distance, and which is also present in the model. So you really have you got the right information in the atmospheric forcing, and you got a good implementation in the model to represent the currents associated to the sea breeze. So it's another, and this about the model capability. Radar, so this high resolution informations about the in the coastal areas. This is the mean circulation you can get from our radar, the SOCIB radar, which is in the eastern part of the Ibiza Channel. So it's a new insight also about the coastal circulations. In that case, you see that WMOP model really overestimate the northbound velocities. It has, in the mean, it has really a much larger velocity than the radar, not exactly the right circulation. You can get complementary estimates of the surface eddy kinetic energy with this data. So complementary to that, we have with the drifters, with the altimetry. And you have here the scales, the radar, quite the same resolution as the model. So you have quite good estimates in the northern part of the area, but here a clear overestimation in this case of the model kinetic energy. And you may want also, you have this full time series of the data, so you can really assess also events in this time series. For instance, this can be plotted or illustrated in terms of Mallorca diagram. You take a section here, you take the meridional velocity, and you see that you really have a high variability, so both in space and time of the signal, and you compare to what you have in the models. In particular, here you can see that you had very strong events in the models, northward events in the models that were not in the observation that may have influenced your mean here, so because you don't have very long time series here. You can compare different models. This has allowed to tell us that we had really too much energy in the model here, in the forecast model, and we changed some parameters or momentum diffusion parameters to correct this. You can compare to the parent model. You can also plot this together with altimetry, showing that, so okay, for altimetry, of course, you don't have this high variability, but interestingly, sometimes you are able to represent strong northward events that are seen in the radar. So even at the coastal scale. So it's like an estimation of other data that can help you to evaluate these northward flows. Okay, so last platform I want to present is the gliders. So gliders, they provide high-resolution hydrographic sections. You may potentially deploy them along endurance line. They're quite low consuming. They're quite slow platforms. They can cover around 20 kilometers a day. But what you can do what we do in SOCIB is just collect data along this endurance line that goes from Mallorca, along Mallorca channel and Ibiza channels, and back and forth during around 1 month. So that you have many transect, high-resolution transect there. This allows you to detect changes or variability in the water masses, and also to compute cross-transport sections. And so you can do that. You can check how your model behaves in terms of these different aspects. You have the section from the salinity temperature from the glider here. This one from the model. You can see already you have this maximum that's not properly represented here. You have this lower salinity water at the surface that are more or less okay, but you can detect differences in the structure. You can plot the temperature salinity diagrams of these different water masses. In particular, for the intermediate water masses, you can really detect biases in the model. You can detect changes. Let's say this one, 13 degrees, what the traditional criterion used to detect the winter intermediate water, and we've seen that in the recent years. This has changed, and the winter intermediate water has now a relatively higher temperature with respect to what it was before. And it allows you to really evaluate long-term also changes in the water masses properties. The leaf, for instance, here, this scorpion tail here that is typical of the Levantine intermediate water is not properly represented in the model. And so this allows you to give feedback to the large-scale model, because all this information is constrained by the information given by the large-scale model. What I want to say here that from this section you can compute the geostrophic velocities, and you can then separate this, compute transports, and separate these transports per water masses. So this is what I show you here. So from the glider, when you have a time series along endurance line, you can have time series and you evaluate variability of the transport across these sections. And you can check whether, for instance, the presence of water masses, in particular, the winter intermediate water that is formed sporadically, not every year, was present during the first year of this time series. This is quite also the same for the model. So we were able to form this water mass and to spread it, propagate it towards the channel. And you can also detect that the kind of variability you have at the short scale, monthly scales, and also here the interannual scale. So it's very rich data set for this. Okay, the summary for this multi-platform validation section. So we've seen a lot of things. We've seen large scale, we have seen different diagnostic, we've seen statistics, events. And in summary, for the multi-platform observations from satellite, ARGO moorings, drifters, radar, gliders, they really provide you multiple indices of the performance of the model at different scales, and both in terms of the statistics, the representation of specific events. So if we try to represent a bit all together different platforms on a single map, this is what you can get from mooring, radar, gliders, different cross-section velocities. And of course, one of the main challenge now is would be the integration of all this information to address specific metrics for specific users. The conclusions. So the model assessment is multivariable, it's a region-dependent, multi-scale problem, and it is constrained by the available observation you have and the specific user needs, specific problems you want to address. So this may require specific measures of the model performance. So there is no magic metric that will give you the one value of the performance of the model. The multi-platform observations provide you multiple indices about the capacity of the model to represent the variability at different scales. So the challenge that I just said is to properly integrate these informations. And from a personal experience, I can say that the operational evaluation of these models continuously adds to the understanding of the model performance. You just add the experience in seeing events, in seeing how the model reproduces what you see day by day. So I let you with some very excellent reference on the multi-platform model assessment. And just to finish, as a local center, I can let you with the forecast for the weekend, and so that you can really evaluate yourself the capacity of the model to represent the water temperature in Poyensa, which is forecasted to be around 23.5. The waves for the weekend, so you had big waves. I think today, then it will be okay. You can go to the southern part tomorrow if you want to be quiet. The wharf gives us the temperature, wind, and rain. And this one to finish is the Rissaga forecast, so there's no significant Rissaga for the next 2 days forecasted by the model. Thank you.
Thanks very much, Baptiste. We have time for a couple of questions. Thanks.
Are results of the model available to the general public somehow?
There is, so on the SOCIB web page, we have systematic validation of all the forecasts. So the forecast of the day before is systematically compared to the observation, and this is available in form of figures, of plots. And then for the specific users, this is not yet available, but I mean, it goes with the use of the models and developing products.
I'm specifically interested in surface currents in the Western Mediterranean.
So surface current, we have the daily maps of the radar available, and you have the altimetry. So if you're really interested in the short-term forecast, this is what you get. Otherwise, you have the long-term validation, the statistics of the currents in the different areas. But as I showed it, there's really multiple indices, so it begins to be more than something you can present on the web page like this.
Okay, thank you.
Thank you. Yep.
What do you use as a boundary condition for the meteorology tsunami, for the weather, for the atmospheric model?
So for the atmospheric model, we use the NCEP GFS model, and we're quite happy at the moment with this. Of course, we also see that we need to run ensembles to have better representation of the results and some probability of this. For the moment, we just take the deterministic GFS and run that model with this.
Thank you.
Okay, the last.
You also use one of here? Okay. Do you also use one of these observational platforms to assimilate the model data, especially, for example, drifter data standard?
At the moment, no, we don't use the drifter. It's maybe the only platform we don't use for the assimilation that is under development. But I mean, it's something we will have to do. So drifters, we don't have a lot of data from drifters. So we have it's really sporadic deployments. We don't always have drifters in the area. So it might help in a given situation with this kind of we can really detect eddies, but it's not a systematic data set we can count on.
Okay, thanks very much. We then switch to our next speaker.